friends, my name is Tushar and today I'm going to talk about how to do range minimum query using sparse table. So what is range minimum query? Let's suppose you are given an array, then you have to find what is the minimum between I and j. So for example, if I is 2 and j is 4, then the minimum between 2 and 4 is 1. Also if I is 3 and j is 5, then the minimum between I and j is 3. If I is 0 and j is 4, then the minimum from 0 to 4 again is 1. So in my video on segment 3, I talked about these three techniques to do range minimum query. If you have not watched that video, I highly recommend you to watch that video. So effectively, if you did a brute force way, then you have to do no pre-processing, but the query will take, in worst case, O of n time to answer. With the dynamic programming, it takes O of n square space and O of n square time to do the pre-processing, but you can give the result back, the query result back in O of 1 time. With segment 3, you can build a segment 3 in O of n time using O of n space, and you can return the result in O of log n time. With segment 3, you can also update the input array. Today, we are going to talk about sparse table. In sparse table, you can create the sparse table in n log n time using n log n space, and you can return the result, the query result back in O of 1 time. In the future, I might discuss lowest common ancestor way. In this technique, you can do the pre-processing in O of n time using O of n space, and you can give the result back in O of 1 time. So next, let's see how the sparse table techniques works. So first, I'm going to show you how to do pre-processing inefficiently. Then we're going to look at how to do the query on that table, and finally we're going to see how you can build this table efficiently. So here we're going to take a two-dimensional array where the number of rows is going to be same as the length of my array, and number of columns is going to be log of n is the size of this array plus 1. So log of 6, the floor of log of 6 is 2, so 2 plus 1 is 3. So which is why we have 3 columns here. Now we start from the 0th row. So our I is 0 and j is 0. What that means is I'm looking for, starting from the 0th guy, I'm looking for the minimum from 0 till the next 2 raised to j elements. So 2 raised to j is 2 raised to 0 is 1. So starting from 0, I'm looking for next one element, the minimum among the next one element. So that number is 4. So I'll store the index of 4, which is 0. Then I'm going to increment my I. So we are going to fill this first row wise. So now my I becomes 1. So again, starting from 1, I'm looking for the minimum among the first 1 elements, because j is 0, 2 raised to j is 1, so I'm looking for the minimum among the first 1 element. So again, that number is 6, so the index of that is 1. So similarly, this will be 2, 3, 4, 5. So now we increment our j to 1 and I again becomes 0. So starting from 0, we are looking for the minimum among the first 2 raised to 1, so 2 raised to 1 is 2, so first 2 elements. So starting from 4, what is the minimum among this 4 and 6? So that value is 4, so index of 4 is 0. So again, this guy will be 0. Now we increment our I to 1. So starting from 1, we are looking for the minimum among the next 2 elements. So 6 and 1. The minimum among 6 and 1 is 1. Index of 1 is 2. So this value here will be 2. So again, starting from 1, we are looking for the minimum among 2 raised to 1. So next 2 elements, and that value is 1 and index of 1 is 2, which is why there's 2 here. So now our I is 2. So starting from 2, we are looking for the minimum among the next 2 elements, because j is 1 and 2 raised to j is 2. So this minimum again is 1, so the index of 1 is 2. Similarly, here among these two guys, minimum is 5, index of 5 is 3, so this becomes 3. Similarly, here minimum of 7 and 3 is 3, index of that is 5, so here we store 5. And finally, for 3, we can't do that because there is no other element after 3. So we stop at this point. And we again go back to the top, our I again becomes 0, and j becomes 2. So now we are looking for the 2 raised to 2, so basically 4 elements. So next, minimum among the next 4 elements. So again, starting from 0, we are looking for the minimum among the next 4 elements. So minimum here is 1, the index of 1 is 2, so this value becomes 2. Again, starting from 0, 2 raised to 2 is 4, we are looking for the minimum among the next 4 elements, that value is 1, index of 1 is 2, which is why this value becomes 2. Starting from 6 till this 7th number, what is the minimum? The minimum here is again 1, so this value is also 2. Similarly, starting from 2, minimum among the next 4 elements again is 1, so this value is 2. And for rest of the guys, it's not important because there are no 4 elements after 5, 7 or 3. So we don't fill them up. Now our j becomes 3. As soon as j becomes 3, 2 raised to 3 is 8, and we don't have 8 elements in our array, so we are done. So this is how we built our sparse table. So next, let's see how we are going to do a query on this sparse table. Let's see how we can get the range minimum query in constant time using this sparse table. So first I'm trying to get the minimum between 3 and 5. So we are looking for the minimum between index 3 to index 5. So first we calculate how many elements are there. So L is equal to 5 minus 3 plus 1, which is 3. So there are 3 elements between 3 and 5. Then we calculate K. K is going to be log of 6 and the floor of this guy. So log of K, log of 3, and log of 3 is 1. So K is 1. So this is what we're going to do. Starting from 3, we are going to look for the minimum of next 2 raised to K elements. So K is 1, 2 raised to K is 2. So starting from 3, we are looking for the minimum of next 2 raised to K elements. And that we have already calculated before. All you have to do is go to 3, which is this guy, index row 3, and then K value is this guy, so index is 3. So index 3 is the minimum from 3 to 4. And this we had already calculated before. And the value at 3 is 5. So we got one value. So the thing is, this covers the 3 to 4, but we are looking for the minimum from 3 to 5. So we are still left with this guy which we have not covered yet. And to do that, we see how many elements are left. To do that, we say L, so 3 minus 2 raised to K, which is 3 minus 2 raised to 1, which is 1. So we are left with one element in the end. To cover that, what we do is we move our start index by 1 from 3 to 4. So from 4, we are looking for the next 2 raised to K elements. We are looking for the minimum of the next 2 raised to K elements. And by doing that, we guarantee that we will include 3 because we moved from here to here by 1. So now, we already got the minimum of this guy, which the value here was 5. And now we get the minimum of these two guys. To do that, we go to 4, 4, and K is 1, so K is 1, so this value is 5, index at 5 is 3, so this value is 3. So we have a minimum from 3 to 4, we have a minimum from 4 to 5, so the minimum of 3 to 5 will be the minimums of these two guys, so that value is 3. So as you can see, this can be done in O of one time. All it took was 2 checks in this sparse table. Next, let's take one more example looking for a minimum from 0 to 5. So how many elements are there between 0 to 5? L is equal to 5 minus 0 plus 1. So total 6 elements between 0 to 5. So K will be log of 6 and this value is 2. So starting from 0, we are going to look for the minimum of next 2 raised to k elements. So k is 2, 2 raised to 2 is 4. So starting from 0, we are going to look for the minimum of next 2 raised to k elements, and that value we have already calculated. So go to 0 and then go to this 2, and that value is 2. So at index 2 the minimum lies. So that value is 1. So we were looking for the entire range 0 to 5. We got till 0 till 3. We have 2 more elements which is not covered. And first we see how many elements we have which is not covered. So L minus 2 raised to k. L is 6 minus 2 raised to 2, so 4. So 2. So we're left with 2 elements. To cover these 2 elements, all we do is from I go 2 further and reach this point. Now from here we repeat the same process, look for the next 2 raised to k elements, minimum of the next 2 raised to k elements. So starting from row 2 or index 2, what is the minimum of next 2 raised to k element? That value is stored here, and that value is also 1. So here we got the minimum of these 2. And you see how moving by 2 we covered these 2 elements which were not covered by the initial range. So now we have the minimum from 0 to 3, and also we have a minimum from 2 to 5. So we are ready to give the minimum from 0 to 5, and that will be the minimum of this one or this one, doesn't matter, and that value is going to be 1. Let's take one last example of 0 to 3. So we are looking for a minimum from 0 to 3. L is equal to 3 minus 0 plus 1, so 4. K is going to be log of 4. So this value is going to be 2. So starting from 0, we are looking for the minimum of next 2 raised to 2 elements, and that value is 0 and 2, so that value is 1. And then how many elements we are left with? So 4 minus 2 raised to k, which is 4 minus 2 raised to 2, which is 0. So we are left with 0 elements. It means that we found the answer we are looking for, and 1 is the answer for minimum between 0 to 3. So as you can see, we can do a query. If we have this table built efficiently, we can do query in constant time. So next, let's see how we can build this table efficiently in and log n time. First thing we are going to do is fill up the 0th column. So our I is 0, j is 0. So starting from 0, we are looking for the minimum of next 2 raised to 0, which is 1 element. So starting from 0, we are looking for the minimum of next 1 element. That value is 4, index of 4 is 0, so this becomes 0. Similarly, starting from 1, we are looking for the minimum of next 2 raised to 0 elements, which is 1. So next 1 element, which value is 6, index of 6 is 1. Similarly, 2, 3, 4, 5. So now our j becomes 1 and I again becomes 0. We are again at the top. So this time we are looking for 2 raised to 1 is 2. So this time we are looking for the minimum of next 2 elements. So 2 raised to 1 is going to be a power of 2, and it can be split into 2 numbers, each of which are power of 2. So in this case, 2 raised to 0 plus 2 raised to 0. Why this is important is because we have already calculated for J0, and we can use that information to calculate for J1. So let's see how. So starting at 0, we are looking for the minimum of these 2 guys. What we know is starting at 0, I have already calculated what is the minimum number what is the minimum of next 2 raised to 0 elements, and that value is here. And then if we skip that many elements, so move forward by one element, at 6 also I have already calculated what is the minimum of next 2 raised to 0 element, and that value is here. So effectively we are just looking for the minimum of value stored at index 0 and 1 while filling this value. So value stored at index 0 is 4, value stored at index 1 is 6, minimum of those two is 4, index of 4 is 0, so this value becomes 0. Let's try one more. So if I becomes 1, j is 1, so we are looking for, starting from 6, we are looking for the minimum of next 2 elements. So again, at 6 I have already calculated what is the minimum of next 1 element, which is stored right here, 1 1, 0, which is 1. And at 2 I have already calculated what is the minimum of next 1 element, which is stored right here, 2 0, which is this value 2. So again what we do is we get a minimum of these two guys. So minimum of 1, so 1 is 6 is at 1, 1 is at a 2. So minimum of 6 and 1 is 1, index of that is 2, so this value becomes 2. Now my I becomes 2. When I becomes 2, again we are looking for the minimum between 2 and 3, and at 2 we have 1, at 3 we have 5, minimum is 1, so this value also becomes 1. Value becomes 2, which is the index of 1. Now I becomes 3. So we are here, minimum of 3 and 4 is, at index 3 is 5 and 7, minimum of 5 and 7 is 5, so this value becomes 3. And finally, between 4 and 5, minimum is 3, index of 3 is 5, so this value becomes 5. If it's not clear, it will get clearer as we move on to the next stage. So j becomes 2. So 2 raised to 2 is 4. So starting from 0, we are looking for the minimum of next 4 elements. Again, what I said before was this 2 raised to 2 can be formed with 2 raised to 1 plus 2 raised to 1. So we are going to use these information to, and we have already calculated them before, so we are going to use this information to calculate for the entire thing. So starting from 0, we are looking for the minimum of next 4 elements. So starting from 0, we already have the minimum of next 2 elements, and that value is stored right here. So at 0 1, this is the minimum of next 2 elements, and then we move forward by that much and reach this point 1, and starting from we reach this index 2, and starting from 2 we have already calculated the minimum of next 2 elements, which is right here. You go to 2 and this 1, so this value is 2. So then we are looking for the minimum of 0 and 2. So the minimum of 0 at index 0 we have 4, at index 2 we have 1, minimum of these two is 1, and the index of that is 2, so this value becomes 2. So as you can see, we calculated this in O of 1 time. So now our I becomes 1. Then starting from 1, we are looking for the minimum of next 4 elements. So again, our j is 2. So we already have the calculated value for the j minus 1. So we go to 1 and j minus 1. J minus 1 value is 1. So this value is 2. This value here is telling what is the minimum from here to here, from 1 to 2, and then we move by that much and reach this point and reach 3, and at 3 we have calculated what is the minimum of j minus 1, 2 raised to j minus, next 2 raised to j minus 1 values, and that value is 3, so that value is here, so we are looking for the minimum of 2 and 3. And at 2 we have 1, at 3 we have 5, so minimum of 2 and 3 is going to be index 2, which is 1, so this value becomes 2. So now our I becomes 2 and we are looking for the minimum of 2 to 5. So again, starting at 2, we already know what is the minimum of 2 and j minus 1, so 2 raised to j minus 1, and that value is stored right here. So we're looking for the minimum of this. So we already have minimum of this, and then we move forward and we look for the minimum of these two guys. So that we already stored right here. So then we are looking for the minimum of 2 and 5. At value 2 we have 1, at value 5 we have 3, minimum of 1 and 3 is 1. So this value again becomes 2. And from 3 onwards we don't have 4 elements left or 2 raised to 2 elements left. So we stop at this point, and here we have recreated our sparse table again, but this time in O of n log n time. So the time complexity for this algorithm is O of n log n. Why? Because the number of rows is n, and if you remember, the number of columns was log of n plus 1. So this is effectively log of n. So the time complexity is n log n, the space complexity is also n log n, and as we saw before, the time for query is constant. So that's how this algorithm has this constant query time and n log n pre-processing time. Next, let's look at the code for this algorithm. So first we're going to look at the code for pre-processing or creating the sparse table. So the method name is preprocess. It takes in the input array and it takes n, which is the length of the input array. Then we declare sparse, which is a 2-dimensional matrix where the number of rows is n and then the number of columns is log of n plus 1, as we discussed before in the video. Then our I goes from 0 till n and we set sparse of I0 as I. So if you remember from before, we took the 0th column and we put the value in the 0th column same as the row number. Why? Because if our j is 0, then starting from every I, the minimum for the next 2 raised to 0 element is going to be that I. So which is why sparse of I0 is I. Then our j starts from 1 till 2 raised to j is less than equal to n. So what this condition here means is that if what we are looking for, if n is 6, in this case we would want our j to go at max 4. At max 2, because 2 raised to 2 is 4 and that's less than equal to 6, so that's good. But if j was 3, then 2 raised to 3 will be greater than 6, and we do not have 8 elements here in this array, so we do not want j to be more than 2. If the size of this array was 9, for example, then we would want our j to go all the way till 3, because 2 raised to 3, 8 is less than 9. So this is this condition, 2 raised to j less than equal to n. Then, so this is the outer for loop where our j will initially be 1. So we are looking for, starting from every element, we are looking for we are looking for the minimum of next 2 raised to 1 element, and then we increment the value of j. So then we are looking for, starting from I, every possible value of I, we are looking for the minimum 2 raised to j elements. So what is this condition here? I plus 2 raised to j minus 1 is less than n. So for example, if the value of j was 2 and if the value of I is say 1, so in this case we should be executing this. Why? Because 1 plus 2 raised to 2 minus 1, so this value is 4. So 4 is less than the size less than 6, so it's okay. So what this means is we are looking for the minimum starting from 1 for the next 4 elements. But if the value of I was 3, then 3 plus 2 raised to 2 minus 1 is 6, and 6 is not less than 6, so we should not be executing that for loop, because after 3 we don't have 4 elements left. So we cannot execute the for loop. So this is that condition. So now if this condition is true, then we go into this if condition, and then we do what we discussed before. We check if input, since in sparse matrix we are storing the index, we check if input of sparse ij minus 1 is less than input of sparse I plus 2 raised to j minus 1 j minus 1, then sparse ij becomes sparse of ij minus 1, or sparse of ij becomes sparse of I plus 2 raised to j minus 1 j minus 1. So whichever of the two is less, sparse ij becomes that value. Again, what are these values? So if j is 2, then this can be split into 2 raised to 1 plus 2 raised to 1. So if our I was say 1 and j was 2, then what we are doing is we are checking, is this guy or this guy, who is the minimum among these two guys, and whichever index is the minimum, that index becomes sparse ij, which is the minimum of these four elements. And then we do this for loop, and then we just return sparse. So hopefully this helps you understand how preprocessing is working. Next let's look at how we do the query. So as we discussed before, finding range minimum query is O of 1 operation. So we're looking for the minimum from low till high. So first L is high minus low plus 1, so number of elements there, and then K is log of L. So then we're looking for the minimum of input of, since we are storing the index there, input of sparse of low till K. So starting from low, what is the minimum of next 2 raised to K elements? That, or input of sparse of whatever number of elements is left, which is L minus 2 raised to K plus low. So we are moving that much from the low, and then from there the next 2 raised to K elements to cover whatever elements are remaining. So the minimum of these two will be the minimum for the range low to high. So this is all I have to talk about range minimum query using sparse table. Please like this video, share this video, comment on this video, check out my Facebook page, and check out my GitHub link. The link to this code is there in the description section of the video. Thanks again for watching this video.